Alright, in this screencast, we're going to be taking a look at the first of two topics in this unit in pre-calculus. And that topic is called Trig Identities. The second topic is solving trig equations, and that's going to be done in a separate screencast. But for now, we're going to look at trig identities. And we start by looking at the trig functions that we defined at the beginning of this study of trigonometry. And so I drew a nice little right triangle here and labeled an angle theta, and then I labeled the two legs A and O for adjacent and opposite, since those sides are adjacent to the angle theta and opposite the angle theta. And then I labeled the third side H for hypotenuse, because that's the hypotenuse of this right triangle. We were given through the definition for three trig functions. So we talk about the sine of the angle theta as being opposite over hypotenuse, or what's really the ratio of those two side lengths. Cosine of theta, which is adjacent over hypotenuse. Again, that's a relationship between the angle theta and then the two sides, adjacent and hypotenuse. And the last was the tangent of theta, which is opposite over adjacent. That gives us a relationship again between theta and those two sides in the triangle. A convenient way of remembering these definitions is this little saying, SOHCAHTOA, which stands for sine, cosine, and tangent, and then it gives you opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. Alright, so those were our basic three trig functions, and again, they relate an angle theta to the three sides of a right triangle, of any right triangle. After we got done looking at those three definitions, we looked at what are called the reciprocal trig functions. And those are going to be secant theta, cosecant theta, and cotangent theta. And they were defined this way. Secant theta is 1 over cosine theta, cosecant theta is 1 over sine theta, and cotangent theta is equal to 1 over the tangent of theta. Alright, and the way I remember these, tangent and cotangent, those are pretty easy. They go together. They're both related to tangent. And then the sine, cosine, secant, cosecant, I just remember that they're the opposite letter. So S and C go together, and then C and S there. So we got those reciprocal trig functions. And the first thing we're going to look at when we look at trig identities is proving something called the Pythagorean identity. And as you can imagine, Pythagorean means we're going to use the Pythagorean formula. So I've drawn another triangle here, labeled an angle theta, and side lengths A, B, and C. And from that, and from previous courses, I hope that we're comfortable writing a squared plus b squared equals c squared. That's the Pythagorean formula, and that statement is true for any right triangle. Alright, now what I'm going to do for the Pythagorean identity, right, is I'm going to write down the trig functions that we just defined in terms of the side lengths of this triangle. So I'm going to say that sine theta is b over c, opposite over hypotenuse. I'm going to say that cosine theta is a over c, adjacent over hypotenuse. And then I'm going to take those two equations and I'm going to multiply both sides by c. So I get that c times the sine of theta is equal to b, and c times cosine of theta is equal to a. Alright, now, using these two new definitions for a and b, I come back to my Pythagorean formula and substitute in for a c sine theta. So there's, a is c cosine theta. Right, so there's c cosine theta, quantity squared, plus, now I'm going to look at b, and b is c sine theta, so I say c sine theta quantity squared, and then on the other side, it's just c squared, so c squared. Now I'm going to square both of these terms, So that gives me a c squared and then a cosine squared theta. I'm going to add to that c squared plus sine squared theta, and then that's all equal to c squared. Now, I'm going to divide both sides of the equation by c squared, and the reason I can do that is because c is non-zero. I know that c is a positive constant. So maybe I'm going to write that over here. Note that c is greater than 0, right? And that's the reason why I can divide both sides of this equation by c squared and be okay. And what I'm left with is the first Pythagorean identity, which is cosine squared of theta plus sine squared theta is equal to 1. All right, so there is our first trig identity. Okay, now what do we do with this? Well, there are two other versions of the Pythagorean identity. So I'm going to say two versions. And the first version happens if we divide both sides of the equation by cosine squared theta. So let me say divide by cosine squared theta. Okay, and if I do that, cosine squared theta over cosine squared theta just gives me 1. Sine squared theta divided by cosine squared theta is tangent squared theta, and 1 over cosine theta is equal to, or 1 over cosine squared is secant squared theta. So there's my first version, or the second Pythagorean identity. And then here, I'm now going to divide by sine squared theta. So there's sine squared theta. All right, and if I do that, cosine squared over sine squared, that just gives me cotangent squared theta. I add to that sine squared over sine squared, which is 1. And then on the right-hand side, I've got 1 divided by sine squared, which is cosecant squared theta. All right, so now what I'm going to say is that Pythagorean identity, that one, and finally this one. Those three Pythagorean identities need to be memorized. You need to know how those work, what those statements mean. I'm not going to ask you to derive them from scratch, but you need to memorize those three equations. And what I'll say is keep in mind that there are also different versions of these if you move the terms around. So for example, let me just come out here and say that I move the sine squared theta over to the right side. So that means that I've got something like cosine squared theta is equal to 1 minus sine squared theta. So that's also true. And I can get that sine squared theta is 1 minus cosine squared theta. And I can do the same sort of manipulation on the other two Pythagorean identities. All right, so those are Pythagorean relationships. The next thing that I want to talk about that you need to know to do trig identities are going to be the cofunction relationships. So cofunction relations. Now, the first thing that I should tell you is, what do I mean by cofunction? Well, a cofunction is going to be pairing up our trig functions. So cofunctions are going to be sine theta and cosine theta. Those will be paired up. We're going to pair up tangent theta and cotangent theta. And we're also going to pair up secant theta with cosecant theta. All right, so we basically have three pairs of cofunction relationships, or cofunctions. And then we need to talk about how these are related to one another. And the idea there is what happens for their complementary angles. All right, so the first thing I'm going to say is that the sine of 90 degrees minus theta will be equal to the cosine of theta, and also that the cosine of 90 degrees minus theta is equal to the sine of theta. Now, there's a proof in your book about why this is true, but let me just say, if you have any doubts, and I encourage you to do this, set up a graph on your graphing calculator where y1 is cosine of theta and y2 is sine of 90 minus theta. And if you make those graphs, you'll see that they overlap perfectly, so that equality is true for any value of theta. Same thing for cosine of 90 minus theta and sine theta. All right, well, those two cofunction relations have to do with our first pair. Our second pair, I'm going to say that the tangent of 90 minus theta is equal to the cotangent of theta, and that the cotangent of 90 minus theta is equal to the tangent of theta. And then our last pair, we'll say secant of 90 minus theta will equal cosecant of theta, and the cosecant of 90 minus theta is equal to the secant of theta. All right, so there are all 6 cofunction relationships. And again, these should also be memorized. I'll never require that you prove them to be true, but you should be able to remember them, memorize them, and then be able to apply them when we start evaluating trigonometric identities. All right, so we've done everything from section 8.4, and so now I want to go through a couple examples to show you how this works. So let's look at example number 1. Okay, all trigonometric identities, the basic problem will look the same. You're going to be given either an expression or an identity. So let's do a version of this called a given expression. All right, so suppose I'm given, let's use an example from the book. This is number 13. So I've got sine of x times cosine of x all over, and then 1 minus cosine squared x. All right, and the instructions tell us that we have to simplify that expression. Well, the first thing I'm going to do is write an equals sign here, okay? And I'm going to look at the numerator and the denominator, and when I do that, I'm thinking about, or I'm keeping in mind, all of the identities that we've just looked at. So if I look at the numerator first, I see sine times cosine, and I'm not thinking there's too much that I can do with that. But if I look in the denominator, I see 1 minus cosine squared x. Well, if I go back up to the Pythagorean identity, we can see that cosine squared plus sine squared is equal to 1. That means that 1 minus cosine squared is sine squared. So in this first step, I'm going to replace 1 minus cosine x, well, cosine squared x, with sine squared x. And I'm going to leave the numerator alone, and that's just going to work out to be sine x times cosine x. All right, well, why was this a good move? In terms of simplifying this, instead of having this subtraction in the denominator, which I can't cancel anything in the numerator with, now I've gotten rid of that subtraction, and I can see that one of the sine x's in the numerator will cancel with one of the two sine x's in the denominator. And just to drive home the point, let's make sure that we understand what sine squared x means. So I still have sine x cosine x in the numerator. Sine squared is really sine x times sine x, meaning that one of these sines is going to cancel and leave me with cosine over sine. So there's cosine x all over sine x. And then thinking about some of my reciprocal trig functions, I recognize cosine over sine as being cotangent x. And now I have successfully simplified this expression, sine x cosine x all over 1 minus cosine squared x, all the way down to just cotangent x. And just to kind of reinforce, well, what does this mean? It means that if I had to evaluate this expression at some value of x, rather than plugging in x for all of these things, finding the sine, finding the cosine, squaring it, taking 1 minus that, and so on, instead of doing all that, I can just find the cotangent of x. And for any value of x, cotangent of x will equal this expression that I was given in the problem. All right, so that's the first kind of trig identity problem that you will be faced with. And so let's do another example. So example number 2. I'm going to be given an equation. All right, well, what does this look like? It looks kind of like what you saw on exercises 29, 31, 33 on page 322. So let's do one of these as an example. Suppose I'm given cotangent squared theta plus cosine squared theta plus sine squared theta is equal to cosecant squared theta. All right, now, when you're given an equation like this, what I'm really asking, or what's being asked, is you need to prove that that equation is true. So I'm going to write that over here to remind myself, prove this is true. In other words, that those things are equal to one another. Now, in order to get that job done, I need to do some specific things, right? I need to start with one or the other side of the equation. So I'm going to let me enumerate these steps here. So start with one side. In other words, the expression that's on one side. 2 is going to be use the identities that we know. So use identities like the Pythagorean identity to simplify or manipulate. And then after you've simplified and gotten the same thing as the other side of the equation, you're done. So get the other side of the equation. All right, so let's see how that works in this example. I'm going to start with cotangent squared theta plus cosine squared theta plus sine squared theta. That's one side of my equation. Now I'm going to go ahead and write an equal sign, and I'm going to think about what this is equal to using the identities I know to be true. All right, well, first thing you might notice is I've got cosine squared plus sine squared. I know that that's equal to 1. So I can write cotangent squared theta plus 1. I'll put an equal sign beneath that. Now, what is cotangent squared theta plus 1? Well, go back up to our Pythagorean identities, all right? And I'm looking for cotangent squared theta plus 1 is exactly cosecant theta, or cosecant squared theta. So we'll come down here and write cosecant squared theta. And now I have an expression here that matches with the right-hand side of my given equation, and so I'm done. Now, I've shown that that equality is true. All right, and so now we can go into all kinds of other more interesting trig identities. And we've seen a lot of practice in class. I've worked several examples in class, and you know that what this really comes down to are things like combining fractions using a common denominator, or foiling things out, multiplying two binomials together, or factoring, or any number of those things. But what I want to say is, aside from all of the algebra that you're doing on these trig identities to manipulate them, so I'm going to say this: strategies, right? The first is algebra, right? You're basically factoring, finding common denominators, doing all kinds of that stuff. And then the second thing, and this is the most important thing, is you can always put everything in terms of cosine theta and sine theta, then simplify. And that should always help you out in getting an expression simplified down to its most basic form. So put everything in terms of cosine and sine, and then simplify it down. Now, having said that, this strategy number 2 may not always be the most effective and quickest way of getting at the answer, but it is going to get you there. It just might take a little while. All right, so that does it for this screencast on trig identities. As just kind of a quick review, let's go back up here to the beginning and say you need to know the definitions of sine, cosine, and tangent, the SOHCAHTOA rule. You need to know how secant theta, cosecant theta, and cotangent are defined. You need to remember the 3 Pythagorean identities. So cosine squared theta plus sine squared theta equals 1. 1 plus tangent squared theta is equal to secant squared theta. And cotangent squared theta plus 1 is equal to cosecant squared theta. And last, you need to remember all of the cofunction relations. And actually, before I forget, let me do a third example with the cofunction relationships, just so you can see how that works. And again, I'm going to pick one out from your book, and I'm going to do, let's see, I'll do number 22 here. So if we look at sine theta times cotangent theta plus cosine theta all over, and then 2 times the tangent of 90 degrees minus theta. All right, and so what I'm asking you to do is simplify this expression. Well, the first thing I'm going to do is write an equal sign, and I might look at sine and cotangent here and rewrite cotangent in terms of sine and cosine. So let's do sine of theta times, now what is cotangent? Cotangent will be cosine theta divided by sine theta, and then I'm going to add to that cosine of theta, all divided by now 2, and now I need to know what is the tangent of 90 degrees minus theta. Well, that's a cofunction relationship, and I know that that's going to be cotangent of theta. All right, well, in the numerator, I can see that the sine thetas will cancel out, and I'll be left with cosine theta plus cosine theta. So that's going to give me 2 cosine theta divided by 2 cotangent theta. All right, well, the 2's cancel out, and so I'm left with cosine theta. Now, cotangent is cosine over sine, so if I want to change this into multiplication, I'm going to flip the denominator into sine over cosine, and then I notice that the cosines cancel out, and I'm left with sine of theta. So this whole expression right here simplifies down to sine of theta. And that shows you an example of using a cofunction relationship. And that takes care of this screencast.